All right, welcome. This is video number 2 for bonding. So for this video, you need to make sure that you have your notes open to page 18. We need page 18 in your notes, and your periodic table would also be helpful for this. And in this video, we're going to be talking about ionic bonding. So what is ionic bonding? Ionic bonding, with the word ion in the title, should automatically tell you that we're going to be talking about ions, and we're going to be talking about things that have charges. We know that opposite charges attract. This attraction between opposite charges is actually called electrostatic attraction. So if you ever see that term, know that that just means the positive being attracted to a negative, and that's all it is. An ionic compound is composed of a cation, which is positively charged, and an anion, which is negatively charged. So an ionic compound with ionic bonding, we have both a positive ion and we have a negative ion. So in this ionic compound, therefore, because we have both a positive ion and a negative ion, what is an ionic bond? Well, it's the force of attraction that's holding these opposite charges together. So ionic compound, ionic bonding, it's a positive thing being held together to a negative thing because they have these opposite charges, because of these oppositely charged ions. That's the bond, the opposite charges holding it together. And we will see an ionic compound. We will know to recognize an ionic compound when we have both a metal and a non-metal together in the compound. And that's what you did in the POGIL types of bonding. You learn that metals and non-metals, when we have those two things together, that's going to make an ionic compound. The metal will always be positively charged, and the non-metal will always be negatively charged. The metal is going to be the thing that's losing electrons. The non-metal is going to be the thing that's gaining an electron. So what happens in ionic bonding? Ionic bonding is based on, we can sort of think of it like a lending system of electrons. The elements that are involved in ionic bonding, they don't have a full octet, but they realize that if they transfer their electrons from one to the other, then each of them can get an octet. So in ionic bonding, and this is a huge, super important point, so you want to make all kinds of stars and circles next to it because it's a really big idea. Your metals will transfer. That's the big verb that the Regents likes to use, transfer. Metals transfer their valence electrons to the nonmetals. So the metal gives up their valence electrons, they give it to the nonmetals. They lose it, the nonmetal gains it, and in doing so, each of them, both the metal and the nonmetal, will achieve an octet. When they transfer their valence electrons, though, that's when we get the charge. Now the metal will have a positive charge and the nonmetal will have a negative charge. Showing you this. So we have sodium and we have chlorine. Notice that sodium, we've drawn the Lewis dot diagram for it here. Sodium only has 1 valence electron. Chlorine has 7 valence electrons. Neither of them have an octet. If you look at their electron configurations, again, that's the 1 valence electron for sodium, that's the 7 valence electrons for chlorine. Neither of them have an octet, so neither of them are energetically stable as is. But, if sodium gives its 1 valence electron to chlorine, now we wind up with these as products. Now we have sodium with now no valence electrons, and now chlorine, with 8, and it has this charge, right? Sodium has this +1 charge, and chloride has this -1 charge. Now, each of these species has 8 valence electrons, because now, instead of sodium ending in 1, we've lost that 1 valence electron, and now its electron configuration is just 2-8, right? 2-8, that's it. Well, bingo, there's the octet. It ends in an octet. And chlorine, instead of ending in 7 here, we've added 1 to it from the sodium. So now its electron configuration is 2-8-8, which is an octet. Again, it is ending in the octet. So now we consider them to be stable. Just quickly, these electron configurations 2-8, notice that this is the same electron configuration as neon. So sodium now has the electron configuration of neon when it's done this. Likewise, it's a noble gas, that's stable. Likewise, 2-8-8, that's the same electron configuration as argon. So chloride, in doing so, has become like argon, so they've become like noble gases. Sodium chloride, an example with ionic bonding. We have this term formula unit that we use to talk about ionic compounds, because in this diagram that you see here of sodium chloride, which is an ionic compound, notice how I don't have individual sodiums and individual chlorides. Like this sodium here is actually sort of attracted and surrounded by chlorides on all sides. Likewise, this chloride here in the middle, it's sort of surrounded by sodiums on all sides. So it's not a single unit. When we have ionic bonding and we have these ionic compounds, it's not just one Na plus and one Cl minus. It's actually a whole bunch of Na pluses and a whole bunch of Cl minuses that have transferred their electrons, and they're all attracted to one another because of that electrostatic attraction, that positive being attracted to a negative. So when we say formula unit, it's the lowest whole number ratio of ions in an ionic compound. Sodium chloride is in a 1-to-1 ratio between sodium and chloride. So we say that the formula is NaCl. It doesn't mean that there's just one Na and just one Cl. It means that they're in a 1-to-1 ratio, because here really it's a whole bunch of Nas and a whole bunch of Cls. And we call this regular repeating pattern a crystal lattice structure. Because it's not random, because it's organized, we call that crystal lattice structure. So ionic bonding. Huge important point. Summing up, ionic bonding is a transfer of valence electrons. We're transferring valence electrons between the metal and the non-metal. Transfer is that really important verb that we use to talk about ionic bonding. So it's made of positive and negative charges, positive and negative ions together. But when you combine them, they're electrically neutral, which means that the charges cancel, right? One positive cancels with one negative. And bonding will occur. The bond occurs because of a very, very strong attraction, not repulsion, but attraction between opposite charges. Now, conductivity. This is a big point. We're going to look at conductivity at several points throughout the year. In order to conduct electricity, there are two requirements. You need to have a charge, and the charge needs to be able to move. So you need a moving charge. So first of all, you need something that has a charge, and you need a phase of matter that will allow it to move. Those phases of matter are aqueous or liquid. In a solid, the charge can't move. So ionic compounds, because they're made of ions, well, that's a charge, right? Ions, by definition, they have a charge. So we have that aspect of conductivity. The ions, though, on their own aren't enough for conductivity. The ions have to be able to move. So when an ionic compound is dissolved in water, AQ, now you have charges that can move. The liquid phase works as well. When an ionic compound is in its liquid phase, now the ions can move and it will conduct electricity. But it cannot conduct as a solid. An ionic compound will not conduct as a solid because the ions can't move. Right? The solid things are locked in place. So, properties of ionic compounds. Again, this is very important. So all kinds of star circles next to these sets of questions. Very, very important. Ionic compounds have extraordinarily high melting points because this attraction between the positive and the negative is such a strong attraction, such a ridiculously strong attraction. It takes a tremendous amount of energy to overcome it. So it takes a lot of energy to heat it up to the point where it will actually melt. Phenomenally high melting points. I'm talking like 300, 400, 500, 800 degrees Celsius, not Fahrenheit, Celsius. 1,000 degrees Celsius to melt an ionic compound. They have a very hard crystal structure. This, again, it has to do with this very strong attraction between the positives and the negatives. Now, these guys are strong conductors, but only in the liquid phase, so that's your L, or in the dissolved phase, so that's the AQ. They do not conduct in the solid form because the ions can't move. Again, it's that moving charge, so that's the liquid or the aqueous. And then just some example questions about properties of ionic compounds that the Regents have asked in the past. We have this one: a substance that does not conduct electricity as a solid, okay, so that's important, but does conduct electricity when it's melted is most likely classified as what? Well, Here, telling me that it doesn't conduct electricity as a solid indicates that the ions can't move, but it does conduct electricity when melted. Well, now the ions can move. So I know that it has to have a charge, but I know that the charge won't be activated until it's liquid. So yeah, that's an ionic compound right there. Doesn't conduct as a solid, but does conduct as a liquid. Yeah, that's ionic compound. Next up, we have this data table. It says it represents properties that are determined by the analysis of these substances A, B, C, and D. Which one is the ionic compound? So first up, if I look at A, I notice it has this melting point of -80 and this boiling point of -20. These are low. These are low numbers. That's not an ionic compound. Ionic compounds have very high melting points and high boiling points, so I know it's not A. Next up, I look at B. Okay, melting point is 20. That's still kind of low. Boiling point 190. Well, that's not too low, but ooh, but it doesn't conduct at all. No, no, no. Ionic compounds will conduct when they are liquids and aqueous, and they will always do that. So if I see that it doesn't conduct, then I know it's not B. Next, we have C, melting point 320, boiling point 770. Okay, well, that's pretty high, so it might be that one. But, oh, look, it conducts as a solid. Ooh, no, no, no. Ionic compounds do not conduct as a solid. They only conduct when they're liquid or aqueous, so it's not C. So we're left with D. So we have these nice high melting points and boiling points, which is very indicative of an ionic compound. And it conducts in solution, not solid. So that's your AQ, and that's what we want. So yeah, choice is D, or choice 4. So that is the end of video number 2. And again, we'll be practicing with this in class the next day.